Hello. Today we're going to cover the method we need to learn for homogeneous linear equations that have constant coefficients. So this is very specific. Homogeneous means that our differential equation is always equal to 0. Linear, we have to remember our rules for linear. We will not see any squaring or cubing or cube rooting or anything on our dependent variable or its derivatives. And all the coefficients must be functions of the independent variable, but even more importantly, they're going to be constant coefficients. Okay, so these three differential equations I've written here, ay prime plus by equals 0, or ay double prime plus by prime plus cy equals 0, or even going to a third order differential equation. All of these equations are homogeneous, linear, and they have constant coefficients. Okay. Now, all of these equations, these are all equations for which we have a linear combination of a function and its derivatives, and it's adding up to 0. What that tells me is that the only function that could be the possible solution would have to be e to the x or e to the mx. Some multiplier of x has to be in there. And the reason for this is as follows. So notice if y equals e to the mx, then y prime is me to the mx, and y double prime is m squared e to the mx. And so there would be some value of m, so that, and with some constant coefficients, if we were to add these all up, we could get back 0 because there's a like term, so the terms will combine. Remember, in order for three things to add together to give you 0, they must have a like term in them. And so also notice if y was equal to x to the m, then y prime would be equal to mx to the m minus 1, and y double prime would be equal to m times m minus 1 times x to the m minus 2. And so now if I try to get some linear combination here of y prime and y double prime, it wouldn't matter what constants I used, there would be a problem because none of these are like terms, right? Y has x to the m, but y prime has x to the m minus 1. That's a lower degree. And y double prime has an even lower degree. So the three terms would never combine. Another would be, notice if y equals, I don't know, sine of mx. Well, then y prime would equal m cosine of mx, and y double prime would equal m squared with a minus sign in front, sine of mx. And so if we tried to get a linear combination of these and get it to add up to 0, that wouldn't work either. The y and the y double prime are like terms. Those would combine, but there would always be a cosine that was left over. So these two, there are no like terms. To add up to 0. And in the first one, all terms are like. And could combine to 0. Okay, so this is how we want to think about our differential equations. Some might call it a guess. It's not a guess. It's very educated. We know our functions. We know their derivatives. Okay, so we're going to use this fact to allow us to assume the form of the solution for all linear, constant coefficient, homogeneous differential equations. All right. So for the second order DE, AY double prime plus BY prime plus CY equals 0, we will begin by assuming that y equals e to the mx represents a solution to the DE. But our issue is that we won't know what m is to begin with. We'll have to find it, and it will be not too hard to do. So here's a set of steps we're going to follow every single time. And in the last step, we're going to end up with cases that will allow us to decide what our general solution looks like. So first, we let y equal e to the mx. Second, we calculate y prime and y double prime. Next, we substitute all three into the differential equation. Then we start factoring. First, we factor out an e to the mx because e to the mx is never equal to 0. We're using a zero product property to solve, and so knowing that e to the mx is never equal to 0 gets rid of one of the non-possibilities, okay? So therefore, it's the quadratic part that's left behind after we factor out e to the mx that will be something we have to solve. Okay, this is called an auxiliary equation, and for no really good reason other than it is the equation that allows us to find m. And really, if you look closely, what we've done here is we've reduced a differential equation with derivatives down to a quadratic equation. And once we solve that quadratic equation, we'll know our m values. So we can either use factoring or the quadratic formula. My advice to you is to be very careful. Factoring is something you've been doing for years. You're probably very good at it, but you've been working with higher order thinking, and so don't trust your brain when it tells you how to factor something. Actually check it. I end up using my quadratic formula quite a bit unless it's very clear what my factors are for my quadratic equation. And so if m is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a, then a very important part that gives us information about our types of solutions is what we call the discriminant. The discriminant is that b squared minus 4ac that sits underneath the radical. If that's a positive number, then that's great. We can take the square root, we get real solutions, and because of the plus and minus on the outside, we have two real unique solutions. And that's going to be case 1. If b squared minus 4ac is equal to 0, then we get real solutions still, but what we get is we get the same solution twice. Because it is a quadratic equation, you have to remember that you would get two solutions. So if you're only seeing one, it's repeating, okay? This is going to be case 2. The third case is when the discriminant is less than 0, and it forces us to deal with the square root of a negative number, and that gives us imaginary solutions. And this will be case 3. So we're going to go through the 3 cases and talk about the forms for their solutions, and then we'll do some examples. So case 1, where we have unique, non-repeated, real solutions, we end up with M1 and M2. I'm keeping everything very generic here. So when we have unique solutions, we can just say, all right, well, y1 is equal to e to the m1x, and y2 is equal to e to the m2x. And then I form the general solution by putting some C1s and C2s in there. And I go ahead and say that my complementary solution is C1 e to the m1x plus C2 e to the m2x. Okay? Case 2, when b squared minus 4ac is equal to 0, I get repeated real solutions. Okay? So here's what that looks like. y1 will be equal to e to the m1x. y2 is also equal to e to the m1x, but we put an x multiplier in next to it. Okay, I'm going to go over why that is in a moment. And then the complementary solution, also known as the general solution in this homogeneous equation setup, just tells us to put in a C1 and C2 and take the linear combination of the two unique solutions. Now, to understand why the x multiplier is there for the second solution, we're going to try using the method of reduction of order, given that we know the first solution is definitely y1 equals e to the m1x. You do not have to do this every time. I'm doing this to convince you, okay? So let's say that we have a differential equation with an auxiliary equation that has repeating roots, and we know one of the solutions. Okay, so we're going to work with y double prime minus 2y prime plus y is 0, and we know y1 is equal to e to the x. Okay, so we're going to realize here that p of x is the minus 2, and so that is replaced in here. We put in a minus 2. We know y1 is e to the x, so I've got that in its two places. Okay, and when I simplify in the numerator of the fraction inside the integral, I get an e raised to the integral of positive 2. And so when I integrate, I get a 2x. And in the numerator, I get e to the 2x. In the denominator, when I square an e to the x, it becomes e to the 2x. And so those simplify and leave behind a 1 for my integrand. And when I integrate it, I get an x. And here's my solution, x e to the x. So when y2 is going to end up being a repeat of y1, an x multiplier should show up. And in fact, if we work with even higher order differential equations and we have more than one repeat, like let's say that we have y1, y2, and y3 all got e to the x, well, then y1 gets to be e to the x, y2 is x e to the x, and y3 is going to be x squared e to the x. So that'll be something that comes up throughout our course. The third case, we need the form of our solutions for the complex problems. In this case, m1 is equal to some alpha plus beta I, and m2 is equal to some alpha minus beta I. The general solution will be written as y sub c equals e to the alpha x. So the alpha was the real part of the of the complex number, and then all in parentheses c1 cosine of beta x plus c2 sine of beta x. There is a derivation of this in the textbook in this section. It's using Euler's formula. The e to the I theta is equal to cosine of theta plus I sine of theta. If you're interested in how our solution becomes a linear combination of sines and cosines, definitely read through that. But for us, what I will stress here is that some people will be tempted to write y1 is e to the alpha plus I beta times x, and y2 is equal to e to the alpha minus I beta x. We do not use these. These are complex valued functions, or I should just say complex functions. Do not use them or use this form. Okay, we want real valued functions, and so Euler's formula allows us to work with exponentials and i's in order to get to the real valued function. Representation of the complex function. Okay, all right, let's look at some examples. In this first one, we're supposed to find the general solution for 4y double prime minus 4y prime minus 3y equals 0. And we're starting off with an IVP. Y of 0 is 1, and y prime of 0 is equal to 5. Okay, so right away, I'm going to let y equal e to the mx, y prime equal m e to the mx, and y double prime equal m squared e to the mx. Now I will sub them in. So I get 4m squared e to the mx minus 4m e to the mx minus 3e to the mx equals 0. I can factor an e to the mx out, and that leaves behind 4m squared minus 4m minus 3. That's all equal to 0. E to the mx is never equal to 0. So now we have our auxiliary equation. It's the 4m squared minus 4m minus 3 is 0. And I'm going to factor this using grouping. If I take the a times c, 4 times negative 3 is negative 12. Factors of negative 12 that add up to negative 4 would be negative 6 and positive 2. So that means I'll rewrite this as 4m squared minus 6m plus 2m minus minus 3 is equal to 0. Okay, so factoring by grouping, I focus on the first two items and then the last two items. The first two terms have a 2m in common, and that leaves behind a 2m minus 3 when I factor out the 2m. The second two terms have a 1 in common, and that leaves behind 2m minus 3 when I factor out the 1. And now I have two terms again. They have a 2m minus 3 in common, and that leaves behind a 2m plus 1. All right, so m is equal to 3 halves, and m is equal to a negative 1/2. So what that tells me here is that y1 is equal to e to the 3x over 2, and y2 is equal to e to the negative x over 2. Okay? I'm not done. It's asking for the general solution, and we have some initial values. So the general solution is y equals c1 e to the 3x over 2 plus c2 e to the minus x over 2. I also need y prime. Y prime is equal to 3 halves c1 e to the 3x over 2 minus 1/2 c2 e to the minus x over 2. All right, let's apply our conditions. Y of 0 equals 1. When I plug in 0 for x, I get 1 is c1 plus c2. And then I have y prime of 0 is equal to 5. And when I plug in 0 for x in y prime, I get 5 is equal to 3 halves c1 minus 1/2 c2. I'm going to take that equation and multiply it by a 2. So 10 is equal to 3c1 minus c2. Okay, now I have two equations and two unknowns. I could actually add them together, and that would eliminate c2. So I'm going to use elimination. Okay, so equation 1 and equation 2, I've got c1 plus c2 equals 1. And then I have 3c1 minus c2 equals 10. When I add like terms, I get 4c1 is equal to 11. Right? And so that is going to give me c1 is equal to 11 over 4. Okay? And then I can substitute that back into either equation 1 or equation 2 in order to find c2. I think equation 1 is easier to work with. And so I'll plug that in here. I get 1 equals 11 over 4 plus c2. So if 1 can be rewritten as 4 over 4 minus 11 over 4, I get negative 7 over 4 as c2. Okay. And then finally, sorry, this is kind of dragging into the last problem. Our general solution is y of x equals c1 11/4 e to the 3x over 2 minus 7/4 e to the negative x over 2. There we go. So that was kind of like everything that you could be asked to do in this section. We have to make an assumption on what the solution looks like, substitute it in, solve a quadratic equation, form our general solution, and then apply the initial conditions. Okay, next one. In this next one, we're told to solve y double prime plus 12y prime plus 36y equals 0. Okay, so we're going to let y equal e to the mx, y prime equal m e to the mx, and y double prime equal m squared e to the mx. And then we're going to sub in, and we get y double prime is m squared e to the mx plus 12y prime, so it's 12m e to the mx, plus 36y, so that's 36 e to the mx equals 0. I can factor an e to the mx out of here. That leaves behind an m squared plus 12m plus 36 equals 0. So now my auxiliary equation that I have to solve is m squared plus 12m plus 36 is equal to 0. And that factors, it's a perfect square trinomial, so it's m plus 6 times m plus 6 equals 0. So m is equal to minus 6 twice. And what that means is y1 is e to the minus 6x, and y2 is x, e to the minus 6x. So we got a repeated root. That means that our two solutions have the same powers of the exponential in them, but in order for them to be linearly independent, we could go through reduction of order to see that an x gets multiplied to y2, but we're not going to do that every time, only the one time that we did before. So then the general solution is just going to be y of x is c1 e to the minus 6x plus c2 x e to the minus 6x. And that's it. All right, next one. We're told to solve y double prime minus 2y prime plus 2y equals 0. So we're going to do the exact same thing. We're going to let y equal e to the mx, y prime equal m e to the mx, and y double prime equal m squared e to the mx. Then we sub these in. We get m squared e to the mx minus 2m e to the mx plus 2 e to the mx is 0. E to the mx is common. We factor it out. That leaves behind m squared minus 2m plus 2. Set that equal to 0. And the m squared minus 2m plus 2 does not factor. Okay, so we're dealing with an auxiliary equation, m squared minus 2m plus 2 equals 0, that won't factor. So I'm going to go straight to the quadratic equation. M will be minus b, so it'll be a positive 2, plus or minus the square root of b squared, so that's 4, minus 4ac, that's going to give me minus 4 times 2, which is 8, all over 2a, so that's 2. And let me just fix that. That means we've got 2 plus or minus the square root of negative 4 is 2i over 2. So m is 1 plus or minus I. Okay. So this means alpha and beta are both equal to 1. And so we can form a general solution using the form that we were given. And it is that y of x is equal to e to the alpha x. Alpha is 1, so it's just e to the x, times c1 cosine of beta x, but beta is just 1, so this is just cosine of x, plus c2 sine of beta x. So again, it's just x. And that's it. That's all we do. We're done with that one. Okay. Now, sometimes we have to deal with higher order homogeneous differential equations, and it's going to bring up some algebra for you. And so I've given us a couple of higher order problems to work through so that we can really focus on solving the auxiliary equations. Forming the solutions won't be too rough. It's, strangely enough, it's the algebra that's the hard part here, okay? So this is a fifth order differential equation, which is going to results in a fifth degree auxiliary equation. Okay, we're going to let y equal e to the mx, and I'm not going to calculate the 5 derivatives. I'm going to plug them in. We know that each y prime has just m as a multiplier. Y double prime has m squared as a multiplier. Y cubed will have m cubed. Y to the fourth will have m to the fourth, and so on and so forth. So we can assume our form, when we substitute everything in, the fifth derivative will be m to the fifth e to the mx plus 5. The fourth order derivative will be m to the fourth e to the mx minus 2. The third order will be m cubed e to the mx minus 10. The second order will be m squared e to the mx plus the first order will be m e to the mx, and then plus 5 e to the mx equals 0. Okay, I'm going to factor out those e to the mx's right away so that we can really focus on our polynomial. So m to the fifth plus 5m to the fourth minus 2m cubed minus 10m squared plus m plus 5, all that's equal to 0. Okay, e to the mx is never 0, so this is only going to be our polynomial that gives us 0. I see 6 terms. Whenever I have an even number of terms, I look to see if I can factor by grouping in any way. So I'm looking at the first 2 terms, and then the third and fourth terms together, and the fifth and sixth terms together. Let's see what happens. The first 2 terms have an m to the fourth in common. That leaves behind an m plus 5. The second 2 terms have a minus 2 and an m squared in common. When I factor out 2m squared, I leave behind m plus 5. The last 2 terms have a 1 in common. When I factor that out, it leaves behind an m plus 5. Okay, so factoring by grouping was definitely the way to go, because now I have 3 terms, and they each have an m plus 5 in common. So I factor out the m plus 5. That leaves behind the m to the fourth minus 2m squared plus 1. So now we're on our way to being factored. The m to the fourth minus 2m squared plus 1 is quadratic in form, and in particular, it is a perfect square trinomial quadratic in form. So the way it factors is we still have the m plus 5, but this is going to be m squared minus 1 times m squared minus 1. Okay? And each of the m squared plus 1s will factor to be m plus 1, m minus 1, and I can write that. So we have m plus 5, and then m plus 1, m minus 1, and then again m plus 1, m minus 1 is 0. So we get m equals minus 5, m equals minus 1 twice, and m equals 1 twice. And so the good thing is that we got 5 roots. If you had accidentally, from the m squared minus 1, just got the m equals 1 twice, you would have had 3 roots, and the indicator that that is incorrect is that we're dealing with a 5th degree polynomial. You've got to get 5 solutions, okay? All right, so the m equals minus 5, that's unique. I don't have to worry about fixing it, but the m equals minus 1 and the m equals 1, I'm going to have to fix those, okay? So our general solution is y of x equals c1 e to the minus 5x plus c2 e to the minus x, that takes care of m equals minus 1 one time, plus c3x e to the minus x. That takes care of m equals 1 the second, minus 1 the second time, plus c4 e to the x, plus c5x e to the x. And that is all she wrote for that one. Okay, so forming the solution was not hard once we had the solutions for m, but most of the work that we had to focus on was just getting that polynomial factored. Okay, so let's see what's going on in this next one that I pulled out. Okay, this is also a fifth order DE, which is going to give us a fifth degree auxiliary equation. And so if we go ahead and substitute everything in, we get a 2m to the fifth e to the mx minus 7m to the fourth e to the mx plus 12m cubed e to the mx plus 8m squared e to the mx equals 0. Factor out the e to the mx, leave behind 2m squared minus 7m to the fourth plus 12m cubed plus 8m squared equals 0. Okay, so the e to the mx is never equal to 0. So our auxiliary equation is 2m to the fifth minus 7m to the fourth plus 12m cubed plus 8m squared equals 0. Right away I can see that there is at least an m squared in common to all four terms, so I'll factor that out. M squared, and I leave behind a 2m cubed minus 7m squared plus 12m plus 8. And that's all equal to 0. Now, that does not factor by grouping. There's nothing I can do to make that nice. However, what you need to remember is that you can use technology to find a root or find a 0 of this polynomial. If we were in college algebra, you'd have to use some horrible theorems in order to figure out what the possible roots are and then try dividing them out. And we don't need to do that. We don't need to do that at all. We're in differential equations. We can simply go to a graph and we can find a rational 0. Okay, so I graphed this. So when I graphed this, I saw m equals a negative 1/2 is a root. Okay, this means m plus 1/2 or 2m plus 1 is a factor. Okay, so depending on how you decide you want to write your factor, if you write m plus 1/2 is the factor, then use synthetic division to divide it out. And let's just recall synthetic division. So with synthetic division, I would write the 0 on the outside. Okay, so the 0 was negative 1/2, so I keep its sign. And then that kind of stays off to the side. I would write the coefficients of the polynomial I'm dividing out of. So that's 2, minus 7, 12, and 8. And that was for the cubic, the square, the linear, and the constant term. If any of those terms was like not in the polynomial, I'd put a 0 placeholder. Then I give myself a little room and draw a bar. I bring the 2 down. And then I take the 2 and multiply it by a negative 1/2 to get a negative 1. Then I add negative 7 minus 1, which is going to give me a negative 8. I multiply the negative 8 with the negative 1/2 to get 4. And then I add the 4 to 12 to get 16. 16 times negative 1/2 is a negative 8. 8 minus 8 gives me my remainder of 0. So this first term is now a squared term. Second is my x, and then this is my constant. So we're dividing a linear factor out of a cubic polynomial. We should have a quadratic left behind. So at this point, what we have is not x's. We have m's in ours. Okay, so an m squared was factored out already. We have an m plus 1/2 that just got factored out. And now what's left is a 2m squared minus 8m plus 16. And that's all equal to 0. Okay, now a 2 could get factored out of that third polynomial. So I have 2m squared times m plus 1/2 times m squared minus 4m plus 8. All of that's equal to 0. Okay, so I have m is equal to 0 twice. I have m is equal to a negative 1/2. And that third quadratic, I can't factor that. I need to use the quadratic formula. So and m is equal to minus b minus a negative 4 is positive 4, plus or minus the square root of 4 squared is 16, minus 4 times 8 gives me a negative 32 all over 2. This gives me 4 plus or minus 16 minus 32 is a negative 16, and the square root of that is 4i. I'll divide it by 2, and this simplifies finally to be 2 plus or minus 2i. So I have all my roots here, but let's look at what happens, because this is just a prime opportunity to review synthetic and long division. So if you write 2m plus 1 is the factor, then you must use long division. Synthetic division can only be used if you have m plus or minus a number. You can't have a constant in front of the m. It doesn't work then. So that's when you have to use long division. So we would be trying to divide out 2m plus 1 from that polynomial up above, which I have its coefficients there. It's 2m cubed minus 7m squared plus 12m plus 8. Okay, so what we do is we focus on the first term of the dividend, and we ask ourselves, how many times, or what would I multiply 2m by to get back 2m cubed? Well, that would be m squared. And that would take the m squared and multiply it through the 2m plus 1. That would give me a 2m cubed plus m squared. And then I would subtract that from the above polynomial. Okay, so it really is the above polynomial minus the one I just wrote. So 2m cubed minus 2m cubed, that just leaves me 0m cubes. So I'm done with those. A minus 7m squared minus m squared gives me negative 8m squared. I bring down the plus 12m and the plus 8. Okay, then I ask myself again, what do I multiply 2m by in order to get negative 8m squared? Well, that would just be a minus 4m. I take the minus 4m, I multiply it by the 2m plus 1 to give me a minus 8m squared minus 4m. I have to subtract that whole thing from the above polynomial. And so that's going to give me a minus 8m squared plus 8m squared. I have no more m squareds. And then the next thing would be the 12m minus the negative 4m would give me 16m. And then I bring down the plus 8. Last time, what do I multiply 2m by in order to get 16m? That would be plus 8. And 8 times 2m is 16m, and then plus 8, and we subtract that whole thing and get a 0 remainder. Okay? So then our original polynomial, we had m squared. We factored out just now 2m plus 1, and then the result, what's left behind, is m squared minus 4m plus 8. So we would be fully factored, just needing to use the quadratic formula again. And then, so we would solve as we did above. Okay, but now we have our solutions. We know what we've got for solutions. M is 0 twice, m equals a negative 1/2, and m is 2 plus 2i. So we've got 1, 2, 3, 4, 5 solutions, and that's what we wanted. Okay, so finally, we can go ahead and write this out. We have y of x is equal to c1 e to the 0 x, oh that's weird, plus c2x e to the 0 x. That is weird, so we gotta think about that a little bit. We'll get there. Plus c3 e to the minus x over 2 plus c4, remember alpha and beta were both 2, so we get not c4 right there, we get plus e to the alpha x, so it's e to the 2x times c4 cosine of beta x, which is 2x, and then plus c5 sine of beta x, which is 2x. And that is our general solution for this problem. Okay. And that's all I have for examples. I hope those last two were helpful in just remembering some really old algebra stuff that you may not have used in a while. It's okay if you forgot something. It's not okay if you don't get help. But I'm trying to anticipate that there may be questions about factoring and division and all those things. But if I didn't answer all the questions, please make sure to reach out for some help.